Okay, so I hope you have figured this out. So this is t prime, right? And what's the norm of t prime? I mean, that's not surprising. It's cosine square plus sine square, which is equal to 1. All right, so the curvature should be easy to calculate now. This is the norm of this divided by the norm of r prime, which we already have right here. Okay, so it's 1 over a. And this is the curvature, right? Now, is it consistent with what we talked about? Yeah, so if the radius is 1, the curvature is 1. If the radius is 10, this is a circle of radius 10, the curvature at each point turns out to be 1/10. Okay, that makes sense, right? It's much smaller because at each point here, if you're driving, you're barely just turning. Okay, now you have to be steering for a long time, right? So I mean, it's going to take a long time to make this whole curve, and in fact, the total curvature, if you add up the total curvature at every single point, it's always going to be 2 pi, regardless of how big the circle is. That's called a total curvature. All right, let's use the second one. All right, or you found r prime. What's r prime? You found r prime is negative. Oh yeah. Oh, I have to say something here. To use for here, okay, for the second formula, we have to use a cross product, right? So that means you want to let r of t be a cosine t, a sine t, 0. Okay, now why do I have to have that? That's the third component. Well, because you're going to do the cross product, and cross product is not defined unless you have a three-dimensional vectors. All right, so r prime, negative a sine t. You already had this, so you don't have to write this down, but I want to put 0 here. Double prime is negative a cosine t, negative a sine t, 0, right? Okay, now let's multiply. Let's do the cross multiplication here because that's what this is called for, right? And that's what is being called for. Let's see, k, and you have to find the norm of r prime cross r double prime. And then you take the velocity and the norm of that speed, and then you multiply that by 3 times, cube it. All right, so if you take the cross product, of course, the first two are going to be 0, 0. Does it make sense? Yeah, because of these two zeros, the first, it's ugly, the first two components will be 0 and 0. Okay, the last component is the only one that matters. All right, this is a square sine square t minus negative, that's going to change to plus, a square cosine square t, and of course that is 0, 0, a square. What's the norm of this? Of course, that's a square. All right, and you know what r prime, the norm of r prime is already. So the norm of r prime is square root of a sine square, square root of a square sine square plus a square cosine square. That's just a. All right, so the curvature is going to be a square over a cubed. Remember, because this has to be cubed, and that's 1 over a. And of course, that is what we found at the beginning. And so that is the curvature at every single point of the curve of the circle of radius a. Okay, so and by the way, I guess I should mention here one more thing. I don't think I'll be asking you much about this, but if you take this 1 over k, right? So that would be the radius, right? And so if you have a circle, let's say if you have any kind of a motion, if you have a motion like this, okay, and right at this point, let's say right at this point, okay, the curvature could be, let's say 5, right? If the curvature is 5, then the circle of radius 1/5 would be the closest it gets to the curvature at this point. Okay, so the curvature is matched, right? This circle is called an osculating curve. osculating circle. So what is an osculating circle? An osculating circle is a circle whose curvature matches the curvature at a point, at the given point of a curve, right? And so an osculating circle, of course, has the radius 1 over k. And so this is the radius of the osculating circle at that point. Okay, for some engineering and design and even the scientific applications, sometimes the osculating circle is a fairly important thing. Okay, and by the way, if k is a big number, you know, like 15 or something, then this will be 1 over 15. That's a really small one, right? If k is very large, like for instance here, this osculating circle will be big because maybe, you know, k could be like 1/10. Okay, if the curvature is 1/10, then your osculating circle has a radius 10, so that's really big. All right, so that is what the osculating circle is. Okay, so I think I'm going to just do one more thing, of course, and then I will quit. All right, so let's go to number 4. All right, so the number 4, this is the last thing we do, and that's capital B. Okay, this is called the binomial vector. And it's quite simple, right? I'll give you the definition of it. Binomial vector is the unit tangent vector cross T, cross N. All right, so what is that? All right, so for binomial, okay? So if T is, let's describe it this way. If T, how should I do this? Okay, well, I will give you a circle and maybe I'll come back to it when I draw this. All right, so let's, I think you can sort of have a good idea, come up with a good idea of what this capital B is doing. Okay, remember, this is a cross product of T cross N. T and N are both unit vectors, all right? So T is like, you know, this one here, okay? N is, remember, it points inward. So I am drawing this in a sense, let's assume that this purple path is the, you know, some animal and bug crawling or something. It's helix, all right? And as you follow the helix path, right, the tangent vector of unit tangent vector shows you which direction you're going. And the principal unit normal vector is showing you where the inward is. So, you know, which direction is inside of that curve. And it's going to go point toward the middle of the cylinder. And B then is, remember, it is perpendicular to both T and N, and it is going to be following the right-hand rule. So if I were to draw capital B in this context here, it'll be kind of going up like this. Okay, so that's my B. What does it mean? All right, so I want you to know T and N are perpendicular to each other. Because B is the cross product of T and N, it is perpendicular to both. Okay, so what we have here is like your X, Y, Z coordinates, right? So this means B is perpendicular to both T and N. Okay, now what's the norm of B? It's the norm of T times the norm of N times what? Cosine of the angle between them? No, it's a sine of the angle between them, right? But what's the sine of the angle between T and N? Well, T and N are perpendicular to each other. It's 90 degrees. So this is actually 1, right? And what's the norm of T? 1. What's the norm of N? 1. 1 times 1 times 1, which is 1. So B is also a unit vector. So we have 3 unit vectors, T, N, and B, all perpendicular to each other. Okay, so this is like your mini small world of XYZ coordinates. Okay, in fact, that is the best way to understand this. All right, so T, N, B make a small local XYZ type of a coordinate system. Okay, so this is actually called a Frenet. It's a French word. Frenet frame, And it's, as I said, it's a mini version of the XYZ axis, or a small local version of the XYZ axis. If you happen to be right here, and if you want to decide your XYZ axis locally, then you use T, N, and B, and those are all perpendicular to each other. And that is your, small Euclidean world around you, okay? And that is called the Frenet frame. And if you listen very carefully to the words said by in the movie Hidden Figure, I think it's the first scene where the hidden figure, the female mathematician, meets the boss, who is at the particular place in NASA. One of the first things they talk about is this Frenet calculation, or Frenet frame. All right, so this all of these are unit vectors, and B is the binomial. And of course, it's easier to calculate than most others, because you have a unit vector here and a unit vector here. I'll give you an example of this. Right? And then maybe, and by the way, if you look at a good calculus book, such as our textbook or Stewart's book, it'll explain, what this T and N and B are going to mean. All right, R of T. Let's say this is helix, just like the picture: cosine, sine, and T. Okay, and then R of T. I'm going to go through this quickly because we've done this many times now. This is 1, and so the norm of this, remember, this is 2. No, sorry, the square root of 2. All right, so T is 1 over the square root of 2 of negative sine T, cosine T, and 1. Right? T prime is square root of 1 over square root of 2, and then negative cosine T, sine T, and 0. Can you normalize this? Well, this is the square root of T. I think the normal vector is easy. We've done this before, but because this part already is a radius of magnitude 1, you can just ignore the constant, and that is your normal principal unit normal vector in this. Notice here, the Z component is 0. So if you look at this blue arrow here, it's actually horizontal, okay? And that's because there's really no change in the vertical speed or the vertical velocity of this motion here. Okay. In other words, this circle is constantly moving. Helix is constantly moving up, and so the Z component derivative happens to be 0. Okay. So N is a horizontal vector here. All right. We have T prime. We have T. Let's multiply T cross N. Can you see this? Maybe you need to highlight this. I like to highlight this kind of thing here. I'm taking the cross product of this and this, right? Using the properties of the cross product, I'm just going to keep that constant out. And then I'll say this is negative sine T. All right, the second one will be what? Negative cosine of T. Okay, and then the last one will be negative sine here. Let me go ahead and write this. It's going to be negative sine times sine and minus let's see, you have this times this. That's negative sine square minus this times this. And so, and of course, I just realized something silly here. I was in a hurry. So when I went from T to the derivative of T, here's cosine, so this should be negative, right? And that should be negative also. Okay, so it's negative cosine, negative sine. So when you take the, when you take this, it's plus sine square minus negative cosine square. So that's going to be plus cosine square T, and that is of course 1. So the answer, this is your binomial. Okay, the binomial is 1 over square root of 2 times the vector negative sine T, negative cosine T, and 1. Okay, and you can see that this is, this is consistent with what this B is. Okay, so for instance, when T is pi over 2, maybe I should say that. let's try to summarize this. At t is pi over 2, that's 90 degrees, you know, since the start. T is going to be 1 over square root of 2 of -1, 0, 1. Okay, and that's the kind of picture I'm drawing here. This is sort of like this t here. Remember the y component appears to be 0, right? Because this is kind of going in the negative x direction. All right, and then n should be perpendicular to it, and it should be showing inwards, so the y component should be negative. And so that is exactly right. If you look at n and then plug in pi over 2, that would be 0, -1, 0. Okay, and again, n is horizontal, pointing inward toward with respect to the motion. And then b is 1 over square root of 2, and then -1, 0, and 1. And so that seems to indicate that it's sort of going the opposite direction. Okay, don't yell at me here. When I changed this to negative, okay, I should have also changed something, because when you take the product t cross n, so you have this times this, and that's going to be a positive sign, right? So this is positive sine t, negative cosine t. I knew something was wrong because my picture wasn't consistent with it. This is a plus. All right, so what does it mean? This means it is kind of going in this direction. You know, it's coming forward. It's coming toward us in the x direction and in the z direction. Okay, so some people think of this as t as, here, let me go ahead and draw this picture again, and I'll explain what I. Okay, so imagine you are like driving, you know, like a pickup truck or something, climbing this, you know, helix path. Okay, so you're going up there. So t, the tangent, is basically the direction that you're going. Okay, and n is the direction that you're turning. Okay, so in other words, at this point, your steering wheel should be kind of moving toward the left because you're turning left, and then b is like your antenna that goes straight up from the top of your pickup truck. You know, like if you look at a police car, they have this big antenna in the middle going straight up, right? So the B is sort of like that. And that's the way you think about this Frenet frame, right? Again, T, the tangent, it's a motion that you are going into. And then N is the way you are steering. And then B is the something that's perpendicular to the road that you're driving on. Okay, so that's you know, that's pretty much what I wanted to show you in section 3. Now, I'm going to tell you, sometimes, you know, things are not as nice as I have been showing you because I have been avoiding ugly pictures, right? And so in just a moment, I'm going to go ahead and pause my recording just to show you how ugly things can get. You don't have to follow me, but watch what happens. Okay, so here's an example, and I have to confess, once upon a time I gave this as an assignment, and students did not react very nicely. Right, so I said, you know, find t and n and b for this, and this was an example in the problem. So I thought, okay, why not? Well, the problem is, all right, so when you take the derivative of this, okay, you get, that's, you know, this is pretty simple. That's fine. But when you take the when you make this, or when you are trying to find capital T, you have to divide this by its norm, and there is its norm. So you divide by it. So here is your unit tangent vector. Okay. Now notice here you have T on the top and the bottom, right? And in fact, the bottom has a square root, which I wrote as 1/2 power. When you take the derivative of this capital T, you have to use the quotient rule for each component. So the first component is 1. I mean, that's not even easy because you take the derivative of 1, which is 0, and then multiply by whatever. And then the next one will be minus 1 times the derivative of the denominator. And the derivative of the denominator looks like this, okay? And then, of course, the denominator is the original denominator square. This whole thing is the first component. The second component is even messy. I didn't even write the third component, okay? So that's what could happen. And so if you have to find, for instance, t prime at a particular number, it's much easier to find, just plug in the number before you work out this general formula. I just want you to know how messy things can be. All right. Now, one last thing here. I think this is a good way to sort of summarize this entire chapter. You remember you start with a vector valued function r, and then you take the derivative. By the way, the right arrow is the derivative, and then the bottom arrow, the going down arrow would be the normalizing. So if you take the derivative, you get the velocity. If you normalize it, you get unit tangent. If you take the derivative of that and normalize it, you get capital N. And once you have all that, and you should do this for pretty much most of the questions you have on homework, then you have t and n together. You can use t and n to find your binomial vector b. And before you find t prime, of course, you have to find t, which requires you to find the norm of this velocity, right? The norm of r prime. And so you use r prime, the norm of r prime, and the norm of t prime to find your curvature, okay? So this is pretty much all you have to remember or think about as you do your exercises in this section. I know this has been a long section, and you have a lot of content in this one section, all right? So you may want to repeat and review parts of these videos, but I hope you've understood everything, and then try to apply what you learn as you do your exercises. So work hard at it, section 3, and then section 4 would be a little shorter than this one, I promise. Okay, all right, I'll talk to you in section 3.4.